Hello, my name is Jawad Ahmed Fareed and I welcome you to our session on understanding n of d1. N of d1 as well as n of d2 are both probabilities that get used in the Black Scholes solution for solving or for finding out the value of a European call and a European put option. N of d2 is an easier probability to understand and is something that we can all relate to. However, n of d1 generally requires a fair bit of discussion. The discussion happens because of its conditional nature. Our objective today is to see if we can build the foundation that is required to appreciate the difference between n of d1 and n of d2. So for today's agenda, we'll start off first with a quick look at the European call option. Then we will play a bit with what we call the generator function. So the Black Scholes equation, Black Scholes Merton analysis, binomial trees and Monte Carlo simulation all assume that there is an underlying process. This underlying process is what we call the generator function, and we'll try and see what we can discern about the shape and form of this function under different conditions. We'll also look at two terms that get used quite a lot in computational finance, and these terms are drift and diffusion, specifically with reference to the function that we spoke about earlier. Once we are armed with these two pieces of knowledge, what does the generator function look like and how do drift and diffusion relate to each other, we will be able to simulate the Black Scholes equation. After simulating the Black Scholes equation, we'll take a second look at n of d2 as well as n of d1 and try and see if we can build some intuition around that. So that's the game plan. If you've ever wondered what Nobel Prize looks like, the equation in front of you is just that. The equation in front of you is the Black Scholes Merton solution for the value of a European call option and can simply be read as S into n of d1 minus x into e minus rt minus t into n of d2. S is the spot price, X is the strike price. Call option gives you the right to buy a security, in this case the underlying share, at some point in time in the future, which is given by time t, at a price that is agreed upon today, which is X. So at maturity, if you bought a call option to buy, let's say, FedEx at 100 and FedEx is trading at 110, you have the right to buy something which is worth 110 at 100. If it is not trading at a level above 100, then you are not obligated to perform. And in essence, that's what the equation tells you. The equation tells you that the value of the call option is equivalent or approximately equivalent to the value of what you will receive if the option is exercised minus what you will pay if the option is exercised. If you look at this graphically, the payoff profile in front of you is a payoff profile of a European call option and or an American call option for that matter, and all it does is plot the values of the difference between st minus x and 0. In this specific instance, because you've paid a premium for the right to buy the call option, your payoff is adjusted for that fact. As long as that premium is not recovered, you don't break even. Once the option crosses the exercise point, it has to move by a small amount to get to a stage where the cost of the premium is recovered, and after that you start making profits on this transaction. So coming back to the equation, the Black Scholes equation assumes that there is an underlying process for the security that we are modeling. What does that process look like? If you're looking at bonds, or if you start with the simplest of securities, you find that the value or the rate of change in the value of the bond is given by a very simple relationship. On the left hand side of this equation, we're saying the rate of change in the value of a bond is equivalent to the interest rate times the principal B at which was invested times dt, which is the time step. We're saying what we're saying is over some time step, over some time period dt, the rate of change in the value of the bond is equivalent to that time step times the interest rate times the principal invested. If you solve this, and you solve this to find the value, not just the rate of change, but the value of the bond at any given point in time, the solution that you see is the value of the bond at any given point in time t is equal to the original principal b naught grown at the grown continuously at the rate of r for a period of time t. So dB equals RBD. RBDT is the process for the change in the value of a bond, and dt is the solution that we tend to work with. So if you plot this graphically, for small values of r, for small values of t, and for small values of dt, the line that you see is going to be a straight line. Now this is very counterintuitive because the function that you see here is not a linear function. The function that you see here is actually an exponential function. As you play with models later on in this course, you'll see that you can get to the exponential function. However, you have to change a couple of things. First, you have to increase the time involved. So in this case, we are only looking at one time step or 1 year. If you increase that, you will see a curve, or you will see the exponential curve that you expected to see originally. You can also see the exponential curve if rather than increasing time, you increase the rate of interest. Because the primary problem is that over 51 steps, the impact is close to linear. So over 51 small steps, the impact to increase the overall time span and the impact becomes significant, you see the emergence of the exponential curve. So one more time. Here's the process. Here's the curve at a small interval of time, with a small interval of time, with a minute impact in value over any given time step, giving you a linear line. And here you get the curve when the impact becomes significant at any given time step. Now, if you look at stocks, so the first process that we looked at, the first process that we worked with was the process for the value of a bond, which is the simplest of process, with no uncertainty, with no unknown element. If you look at the process for a stock, a currency, a commodity, an index, or any other security that has some element of uncertainty built into it, the process is slightly different. So first half, the first piece is very similar to the process that we saw for the bond, right? We are saying rate of change in S is equal to mu S dt plus sigma S dz. The mu S dt is exactly the same as RB dt. The only difference is R has been replaced, the rate of return has been replaced by mu, some rate. The principal invested B has been replaced by S, the original value of the security in question. Dt is the same as dt. The only additional piece that is now here in this process, in this equation, is sigma S dz. Now, if you look at the impact of this from a solution point of view, the solution is a little more complicated. However, if I were to draw parallels, I'd say, okay, I have S naught, I have B naught, that's fine. I have exponential here. Now, the only thing that's different in the first term is mu minus half sigma squared. And in the solution for the bond, I have R. So where does mu minus half sigma squared come from? What we're really saying is that when you add uncertainty, when you add the element of sigma, the return of the expected return of the process, the expected return on the underlying security, is a function given by mu minus half sigma squared. Not just mu times t, but mu minus half sigma squared times t. This minus half sigma squared times t is also known as volatility drag. In essence, saying that if you have securities that have very high volatility compared to the rest of their peer group, then over a period of time it's possible that the long-term trend would be downwards. Or alternatively, in essence, what we're really saying is that beyond a certain threshold, volatility tends to eat into the return that is being generated. The second piece of this equation, the sigma under root t zt, this is the piece that actually introduces uncertainty. But as far as the first piece is concerned, I would say that except for the change, which is mu minus half sigma squared, everything else is similar to the solution that we've already seen for the bond. The only question that I would ask now is, what is the impact of this additional term? The impact of this additional term, if you go back to, there you go. So that's the graph that you see for the price of a bond, small intervals. Here's the graph at large intervals. You've added a term for volatility. If you look at the impact, if you imagine the impact, what would be the impact of this additional term? The impact of this additional term is that while the long-term trend is still positive, however, there is now elements of uncertainty. Things go up, come down, go up, come down, go up, come down. So quickly, here's the trend with volatility, with uncertainty. Here's the trend without volatility, without uncertainty. Certain, uncertain. So let's conduct a couple of thought experiments. We've just made some very broad assertions about how the Black Scholes equation works, as well as the underlying process that we use to simulate the behavior of a stock price or a share or an index or a currency or a commodity for that matter. Let's ask ourselves some very simple questions and see what we can learn from the last two lessons that we've just presented in front of ourselves. What happens for different values of mu or r or sigma? Before we move forward, there is one concept that we have to introduce, and that concept is the concept of risk neutrality. So the Black-Scholes analysis, as well as the work that we do on the binomial side, assumes that the world that we work and operate in is a risk-neutral world. What do we mean by risk neutrality? Risk neutrality, in the simplest of sense, suggests that in a risk-neutral world, all investors, irrespective of their risk preference, are happy with one single rate of return, and that rate of return is the risk-free rate. Now, this also suggests that all assets grow only at the risk-free rate. So investors earn the risk-free rate, assets return the risk-free rate, grow at the risk-free rate, and the entire world operates on the basis that risk preferences, the amount of risk, does not enter into the question of return. So if we apply this concept to the equation that we just seen, you can see that where we had mu, we simply replaced mu by r, the risk-free rate, and in the solution also we've replaced mu by r, so it now becomes s naught e r minus half sigma square into t plus sigma under root t times zt. Now let's conduct a couple of very quick and very short thought experiments that allow us to understand the difference, allow us to understand the application of what we've just done here. There are two terms that I am going to quickly introduce. The first term is what I call drift. So drift is the long-term trend. Drift is the long-term return. The second is diffusion, which is volatility, also known as dispersion, also known as standard deviation. So in the series that we saw here, the long-term trend is positive, and you'd say, the drift is positive, the drift is upward sloping. In this sequence here, while the drift is positive, there is some indication of uncertainty, there is some indication of what we call diffusion, sigma, standard deviation, or volatility. So a thought experiment is an experiment that allows us to ask some very simple, very basic questions, which put what we just learned in context. Let's start with the first one. So if I were to look at the equation that we introduced as the primary process or the generator function behind the Black Scholes analysis, what happens when I turn r to 0 and I turn sigma or standard deviation to 0? More importantly, what does the graph, the plot of prices that we'd seen earlier, what does that graph look like? So take a second to think about this. If you were to plot prices over a period of time and vol was 0 and r was 0, what would the underlying series look like? There you go. So if you assume that spot prices are at 9 when you started this exercise, and you assume that r, the risk-free rate or drift, is 0, and volatility or sigma or standard deviation or diffusion is 0, then all you get is a flat line that stays static at 9. So the asset is stuck at 9. It's not growing, it's not moving, it's not going anywhere. Why? Because both the risk-free rate of return, the drift, as well as the volatility are 0. Next experiment. So now what we've done is we've switched standard deviation or sigma or drift or diffusion, sorry, standard deviation, sigma or diffusion with 0, and we've switched r or drift by 1. So in this case the risk-free rate is 1 and volatility is 0. What happens now? There's the equation. You plug in r equals 1 in this equation. What kind of results do you get? So once again you can see that the line that you see is a sort of a linear line, but an upward sloping line, and it's growing at some rate, which is the rate that has been given here. If you move on to the third thought experiment, in this case we're saying let volatility remain at 0. What rate of r do you actually see a curve? So in the previous line, in the previous curve, in the previous graph, you saw a straight line. What rate of r gives you an exponential curve? And is it just r, or is it also time? Is it just r? Is it also time to maturity? Is it just r, or is it also time step that is being used as far as the underlying simulation of the price series is concerned? Now, what level of volatility? So R is 1 and we've now introduced some volatility. We don't know what that number is. Our question is, we have positive volatility, but we will now see two graphs very, very quickly. The first graph that you see also has volatility. When you introduce volatility, you can see that there is an impact. But interestingly enough, the question that I really want to ask is, what level of volatility, at what threshold do you get to a point where the long-term trend becomes negative? The long-term trend of the price becomes negative. Positive trend, negative trend. And the primary difference is, but yes, while R is equal to 0, but the primary difference is that there is some threshold of volatility at which the long-term trend will turn negative. So if you were to go out and build this model in Excel, you need to first build a slightly stronger intuition of how the Black Scholes solution or equation could be read. One way of reading this equation that you see in front of you is what we have in front of us, which is, look at SND1 as the amount that you would receive if the option is exercised, and look at XE minus RT minus T into ND2 as the amount that you will pay if the option is exercised. In statistical, computational finance, and actuarial sense, we say we're looking at the expected present value of the receipt and the expected present value of the payment. When I say expected present value, I'm saying I've adjusted the payment for not just the discount factor, but also the probability of occurrence. So in addition to the discount factor, there is also the probability that the option will be exercised, and both the discount factor and the probability are reflected in the receipt. And same goes for the payment. That's one way of looking at the Black Scholes solution. Another way of looking at the Black Scholes solution is to actually break this down into two separate options. We've heard of exotic options, we've heard of binary and digital options, options that give a specific payoff if a certain event occurs and give nothing if the event does not occur. So in this universe of binary and digital options, you have two specific categories. The first category is what we call an asset or nothing option. If the event occurs, what is the event? The event is ST is greater than X. Remember, this is a call option, so A call option only gets exercised if ST is greater than X. So if ST is greater than X, I get the asset. What is the asset? The asset is Sn d1. So if the option is exercised, I get Sn d1. If the option is not exercised, I get nothing. The asset or nothing option is an option that will deliver the value of the asset at the future date in time when the option is exercised. The present value of that payoff is Sn d1. Why is it Sn d1? It's something that we will talk about a little later. But for now, let's assume that the asset or nothing option, the present value of the asset or nothing option is what you see in front of you, which is Sn d1. A second type of a digital option is an option that does not deliver the asset. This is an option that delivers cash. So if the event happens, I win $1 million. If the event happens, I win the strike price. So in a cash or nothing option within the same Black Scholes analysis, what we're really saying is if ST is greater than X, I get a known amount. What is that known amount? That known amount is the strike price. And I get, in today's term, I effectively get the present value of that known amount. So another way of looking at the Black Scholes equation is to say that a call option, a European call option, is actually equivalent to a long position in an asset or nothing option that delivers S if ST is greater than X, and a short position in a cash or nothing option that requires you to pay X if ST is greater than X. The difference between the two will give you the value of the call premium. So that's description number 2, or interpretation number 2 of the Black Scholes solution. A third interpretation, or a third view, or a third point of view is that Sn d1 is effectively the hedge ratio, which is basically delta times S. So this is the amount of that I need to have in order to protect myself if I am the person who's written the underlying call option. If I've written a call option on S and I want to protect myself, I want to cover myself, I want to create a synthetic replicating portfolio that mirrors the value that I would end up paying to the buyer of the call option if and when the option is exercised, Sn d1 is my hedge. Now the problem is, if Sn d1 is my hedge, the call premium that I've received is not enough, is not sufficient to cover that hedge, which basically means that I need to now go out and borrow the difference between Sn d1 and call, and that difference is x e minus r t minus t n into d2. So a final variation on our read of the Black Scholes solution is that the first side, the first element, the first step, the first piece of the equation is simply the hedge ratio delta times S, and the second piece is the amount that we have to go out and borrow. It's the amount that we have to go out and borrow to finance the hedge so that we can cover ourselves, that we can cover the risk of the option exercise if and when the option is exercised. So now all of this leads to a lot of, you could say, questions or confusion around what exactly is the difference between ND1 and ND2. So ND2 is very clear. From an analysis point of view, from a mathematics point of view, what are we saying? We're saying I will pay X at maturity if ST is greater than X, and I can simply use this description or this definition to deduct or assume that as far as ND2 is concerned, as far as the Black Scholes analysis in the risk-free world is concerned, ND2 is the probability that ST will be greater than X, or that the option would be exercised. Question is, what is ND1? If this is what ND2 is, what is ND1? So now to answer this question, we have to dig a little deeper. And the example that I'd like to give is a very simple example that comes from basic mathematics. Let's assume, or let's look at a normal fair die. So it's a dice that you would roll, and this dice has 6 faces. Each of those faces has a number on it, 1, 2, 3, 4, 5, and 6. Each of them is equally likely to occur. So if you look at ND2 and you say ND2 is the probability that ST is greater than X, let's assume that strike is set, or X is set at 3. So we're saying, what is the probability that ST is greater than X? Now the unconditional probability that ST is greater than 3 is, there how many numbers greater than 3? 4, 5 and 6. So when you roll a die, there are 6 possible events. 3 of them are greater than X, or the strike price, or 3, and hence you can assume that the probability is 4, 5, 6 divided by 1, 2, 3, 4, 5, 6, which is 3 possible events, 3 possible instances where ST could be greater than X, divided by 6 possible instances that are likely to occur when you roll the dice. This unconditional probability is ST greater than X, right? That's one. Now, what is ND1? ND1 is a little different. ND1 is a little different in the sense that you're saying, I only want those values of ST. My primary interest is in those values of STs where ST is of those values where ST is greater than X. So in the first instance, we were saying, what's the probability that ST is greater than X? That probability is um, 3 by 6. The conditional probability that we're now looking at, we're saying what is the probability that ST is greater than X given that ST is greater than X? Or what, sorry, my mistake. What is the value of ST given ST is greater than X? So in this case, the number that you look at is how many numbers are likely that are likely to occur that are greater than X. 4, 5 and 6. So 3. When you roll a die, any one of them may occur. So if I tell you that ST is greater than X, and I want to know what is the probability that ST will be greater than X given that ST is greater than X, then that number is any one of these 3, which is 4, 5 and 6, or 1 by 3. That's one way of looking at it. A second way of looking at it, what is the value of ST? What's the expected value of ST if ST is greater than X? So in the first instance, I was looking at probabilities, now I'm looking at expectations. The expectation that ST is greater than X on an unconditional basis, without any conditionalities attached to it, is simply the average of 1, 2, 3, 4, 5 and 6. So if you simply sum these numbers, 1, 2 and 3, so 1 and 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10, 5 is 15, 7 plus 6 is 21. So you have 21. How many values do you have? You have 6. So 6 by 21 is the average value. 6 by 21 is the value of ST, or is the expectation of ST. But if I now say that I am only interested in the value of ST when ST is greater than X, I only have 3 values. What are those 3 values? 4, 5 and 6. If I sum these, I have 15. If I divide these by 3, I have 5. So you can say that the number of the expectation of ST on an unconditional basis is under 5, but the expectation of ST given ST is greater than X is exactly 5, and that's the difference. So what you're really saying is, what's the difference between SND2 and SND1? The primary difference is SND1 would be somewhere about 4.5, 4.6, or somewhere between 4 and 5, but certainly below and under 5, and SND1 would be 5. Right? So that's 2. Now, if I actually get into this, what I'm really saying is X into PV into ND2 is the expected present value of payment, and that basically means that ND2 is the probability that ST is greater than X, or the options exercised. If I compare this with SND1, I'm saying SND1 is the expected value of the underlying that you would receive given ST is greater than X, and if and only if the option is exercised. So what you're saying is, find out the expectation of ST given ST is greater than X, multiply that by the probability that ST is greater than X, and you will have your expectation. You will have your SND1. If you simply play with this equation just a bit, and you move divided by S on both sides, you actually get ND1 is simply the expectation of what you would receive if the options exercised divided by S, or the ratio of what you would receive if the options exercised divided by S. So I hope that this has sort of set the basic context of what we're talking about when it comes to the difference between SND1 and XND2. However, given the conditionalities involved, sometimes it's quite easy to get confused and lost, which is the reason what we've done, or what we suggest, is that rather than stopping here at a theoretical discussion or at a theoretical level, let's try and see if we can set up an Excel spreadsheet that allows us to numerically walk through values for both ND1 and ND2. And when we have these values, we can then try and see that if we look at the relative changes in both values over a period of time, or a set of values, or a set of prices for the underlying, what kind of intuition can we build that would allow us to better understand the difference between ND1 and ND2. So when I go and build this model in Excel, I have to make a number of assumptions. What I'm going to do is I'm going to build a Monte Carlo simulator in Excel that will simulate the underlying stock price. It'll also simulate the Black Scholes equation, and it'll also simulate the results of this analysis. For the model to work, I have to go out and define a handful of formulas. So the first formula is expectation of ST. Right? What is expectation of ST? Expectation of ST is simply the average of all simulated terminal stock price. So if I generate a path using Monte Carlo simulation, and that path has 51 steps, the value of S at the 51st step will be ST for one single iteration. If I repeat the Monte Carlo simulation 10 times, 20 times, 30 times, or 100 times, I will store the value of ST those 30 times, and then I will simply take the average of that. So I call this, on one side, on the left hand side, I call it E of ST, or expectation of ST, and I will simply label this as A. Now my second piece is the probability that ST is greater than X, or ND2, and this is simply for each of the runs that I've stored, or each of the simulations that I've run. This is simply a count of all the instances when ST was greater than X, and I simply take this count and divide it by total simulation, and I call this B. The third piece is, what is the value of ST when ST is greater than X? And this is simply an average of ST for each simulation when ST was greater than X. And here we go back again to the example of the dice that we covered earlier. The expectation of the dice of S when the dice was rolled, given ST was greater than X, was 5, which was more than expectation of ST, right? And we call this C. Now we take this expectation of ST given ST is greater than X, you multiply it by probability of ST being greater than X. So what we're doing is we're taking what we call C, and we're simply multiplying C by B. S and D1 in the sheet would then be the value of D times the PV factor, and ND1 would simply be the value of D times the PV factor divided by S. So this is one set of formulas that I've defined that I'll go ahead and implement. Now let's take a look at how does the model look. So to build this model, I actually need 3 or 4 pieces. The first piece is a set of assumptions and inputs. These assumptions start off with what's the spot price is 9, what's the strike price is 10, volatility 10%, time to maturity 1 year, risk-free rate of 1%, 50 steps, a delta T of 9.02. So in essence, what I'm trying to do is I'm trying to use a Monte Carlo simulator to price the value of a European call option struck at the strike price of 10 on an underlying whose spot price is 9, with a volatility of 10% and a time to maturity of 1 year. The risk-free rate is 1%. The paths that I simulate are 50 in total, giving me a time step of about 0.02. When I run the simulator, I see a handful of results. I get ST, which is the final price. I also track and look at a logical test, which is ST is greater than X. I look at expectation of ST, unconditional expectation of ST, as well as a conditional expectation of ST. And you can see that for the run that we did when we took the snapshot, expectation of ST was 9.06, unconditional expectation of ST was 9.06, conditional expectation of ST was 10.41. Then we also calculate minimum ST, maximum ST, and average ST. That's one part of the model. We put in an input, we get a path, we get some values. The second part of the model basically calculates and stores a handful of results, and those results are the same numbers, same formula, same calculation that we've seen earlier, which is what is x into PV factor into ND2, what is SND1, what is ND1, what is ND2, what is the value of the call premium by using Black Scholes and Monte Carlo, what is the value of the call premium using pure simple Monte Carlo, what is the call premium at a given or current iteration, and then we go out and calculate the results that we've spoken about earlier. So that's the second piece. The third and final piece is what I call the result warehouse, which is where here's my model. This model generates a path as well as gives me a value for ST. I store this path in this results warehouse. My mistake. I don't store this path. I store ST, the final value that's generated by the path. I store that path here. I also track whether the value of ST is greater than X, and that becomes the second column. I also track the value of ST when ST is greater than X, and that becomes the third column. And I also track the call premium, which is the present value of the exercise. So in this case, if you see, if I look at element number 2 or cell number 2 or row number 2, you can see that ST is 11. Now the spot price is 9, the strike price is 10, which means that the payoff on this specific contract is $1. However, I get this $1 at maturity, at the end of 1 year. To figure out what is it worth today, I need to discount it. I discount it using the PV factor, and the number I get is 0.99. So the call premium is the value, is the number that I store at that point in time. If I work this through, then all I'm doing is I'm storing ST, I'm calculating whether ST is greater than X, I'm calculating the value of ST when ST is greater than X, I'm calculating and storing the call premium, and I run this X number of times, whether that's 15, 20, 30, 100 or 1000 iterations and simulations, and then take it from that point in time.